Yeah. Okay. So I'm going to talk about the extensions to the object constraint language. Now, object constraint language is the standard semi-formal or formal language that's used to constrain object-oriented models in the UML standard. It's used also in other ways. It's used in transformation languages and variant versions of OCL, such as the epsilon object language, are used in other specification languages. So OCL is a very significant language which is used across the world. But in the current version of the standard, version 2.4, there are not any map or function types. Although most programming languages do support such types. And those are not just useful at the implementation level, but map and function types can also be useful at the specification level. For example, to specify higher order functions, to specify generic functionality using functions as parameters and so on. We can also use it for design, so maps are useful to specify the caching of operation results and functionality, for indexing objects and for many other purposes. Now, it's beneficial to have the same facilities at the specification language and the implementation level, because then the developers have a consistent view between the specification level and the implementation level. There's not a major discontinuity between those two levels. So what I'm proposing in this paper is a way of consistently extending OCL with both map and function types. OCL is a textual language. It's used to specify constraints on the graphical models like class diagrams and meta models and many other notations. It has the usual basic or primitive types of strings and numeric types and booleans. And when it's referring to a particular model, like a class diagram, we can also refer to the classes and enumeration types of those of that model in the OCL formulae. There are collection types, and the collection types are essentially ordered and unordered collections of various kinds. And as a universal type, OCL, any. So the type system looks like this, where we have OCL any as the universal type. Everything is an instance of OCL any. We have collection types, we have tuple types, objects from the object classes from the model, enumerations from the model, and then the primitive types. And at the bottom, we've got some types to deal with invalid values and null values. Well, maps are fairly obvious what a map has to be. It can be represented by means of a type constructor in the OCL style. So instead of having sequence with one parameter, we have map with two parameters, those parameters being the key type and the value type. And of course, there's the constraint that key values must be unique. Now, we could think of this in terms of the existing OCL by saying that there's an underlying set of each map, and that underlying set is a set of tuples with the first element in the key type and the second element in the value type. We could also represent that as a maplet in actually Z notation, first mapping to second. And then a literal map can be written like that. There's many operations, many applications of map types. First of all, we could use maps to represent the caches of operations in order to make operation execution more efficient. So if we're doing a computation, say, of a factorial function, then we might have lots of repeated computations in a simple recursive version of that function, of that operation. We can avoid that repetition by using a cache of values that are already computed. Likewise, if a class has an identity attribute that's used to look up objects by key, then we can also represent that situation by a map. Maps can be consistently added to the semantics of OCL. In the OCL standard, there's an Annex 8.2, which describes the semantics of all of the OCL elements, and we can simply add a map type to mean that maps are finite functions. That's this symbol, finite functions from the interpretation of the source type, the key type, to the interpretation of the target type, the value type, and there's a null map or invalid map. Invalid elements represent essentially an exception, some exceptional situation. Now, maps can be considered to be a subtype of OCL any, so this type structure that we have here still makes sense if we add a map type. Maps are not collections, they're going to be essentially the same status as a tuple type here, but they're going to be they could be subclasses, a subtype of OCL any. That's not entirely straightforward, because although we could, for example, map this type, we could interpret, say, map OCL any to string as a subtype of OCL any. That's not an obvious embedding, or it's not a unique embedding. So it's not a simple subset relation, that subtyping relation, but it can be done. There's many operations on maps. One basic one is to take the set of keys. Another one is to take the set of values. And another one is to evaluate a map at a given key value. If the key value is not in the map, then the result is the invalid value of t. Now, in our work, we're very concerned with the code generation from OCL, and we have a tool set called Agile UML, which does code generation in multiple languages. So this proposed OCL type of maps can certainly be implemented in almost any programming language. For example, in Java, it's a map type. In Swift, it's a dictionary. In C++, it's a map type, and so on and so on. And also the operations have direct interpretations. Python also has direct implementation. The only tricky one is C, because in C we have to essentially handcraft a map in terms of trees. Now, maps are fairly straightforward, but function types create semantic problems for the type system of OCL. Function types are, again, quite widely supported in programming languages. They support functions as first-class values. In other words, functions can be passed as inputs to other functions. They can be created by a functional abstraction like a lambda expression, and so forth. These are now present in most languages. They weren't present in early versions of Java, but they are now in Java 8 and subsequent versions. They have different names in different languages, like closures in Swift, but the essential concepts are the concepts of lambda expressions. So we can define an extension of OCL, at least in principle, by saying we've got a function type from S to T for any types S and T. And these are the types of partial functions. In contrast to maps, they are immutable. So once you define a function, you can't change it. Now, even those immutable functions don't fit very well into the OCL type system. Functions are very useful. Function types can be used to deal with genericity, to have higher order operations where we can have a parameter which can be itself a function, so that our higher order operation can apply to a whole range of different functions. And for example, an optimization procedure like a secant which searches for a root of a given function and it's generic in terms of that function. You can supply any real-to-real function to that optimization procedure, and likewise with evolutionary algorithms. So function types, again, can be given a semantics in terms of partial functions from the domain to the range. In contrast to maps, as I say, they're immutable, and they can also be non-finite because they're not given by an explicit enumeration of the mappings, but they're given by an expression, by a computation. And as is familiar, the cardinality of the function space from S to Boolean is greater than the cardinality of S. So if we allowed OCL to be an argument in the domain of a function type, then we would end up with a contradiction. So we have to restrict the construction in some way. What we chose to do in Agile UML is to remove OCL. There are other possibilities, but if we remove OCL, then we're allowed to have function types from any of the types that you see here. So the type system is essentially the same as before, but with the addition of maps and functions and the removal of the superclass, the supertype. Okay, operational functions, fairly straightforward. Application, of course, and again, this returns an invalid value if the function isn't defined on the X. Lambda abstraction, lambda x of S in E defines a function from S to the type of E, and is defined by the evaluation of the expression E on the value on the source. Now, that's very similar to the existing let expression that's in OCL and UML. And in fact, a let expression could be seen as an evaluation of a lambda. Again, this can now be implemented in most current programming languages with quite widely varying notations, but they all support some form of function type, some form of lambda abstraction, and of course function application. Even it's possible in C, but with some restrictions. So in conclusion, we can say that map types can be added to OCL without really disrupting the existing type system of OCL. And that is part of a proposal, in fact, for the next revision of OCL, although it's not clear when that next revision is going to happen. However, for function types, there is much more disruption of the type system, and in particular, if we retained OCL as this universal supertype, then we couldn't have OCL in the first argument of a function type. Or we could have OCL just as a supertype of non-parameterized types, so of the different kinds of classes, for example, as a universal class. Or what I've chosen to do is to remove OCL from the type system altogether. The disadvantage of that is that it prevents you to form collections made out of, say, strings and objects and numbers and disparate kinds of things. Okay, so that's the presentation.
Okay, thank you very much for the nice presentation. If there is any question, we can take it in the chat box, or you can raise your hand. Okay, so okay, there's one question. How do you deal with inheritance of function types?
It follows the normal covariance, contravariance rules, in that if you specialize the target type, then you get a specialized type. and vice versa for the domain type. So there's a natural definition of subtyping between two different function types based on the subtyping of the domain and target type.
Okay, thank you. So can you elaborate a bit on pros and cons of adding more details to the UML OCL? Like you talked about a bit about the advantages, but are there any disadvantages of adding more details to the UML OCL?
Well, it makes the languages larger, of course, which means that any tool that uses these languages, they have to be adapted to deal with these extensions. And in particular with things like code generation, if you want to code generate for the whole language, then this means that you have to define an interpretation of these extensions for every potential target language. So there is a downside to extending the language, but my overall view is that these are extensions which are very useful, and it's essentially a situation that OCL needs to be updated in line with the general progress in programming languages. So 20 years ago, when OCL was initiated, function types were not a normal feature of the mainstream programming languages, but now they are. And the software engineers, the practitioners, take these for granted, and it's a major mechanism in languages like Swift and mobile technologies and so on, having function types and closures. So I think OCL has to be updated, really, even though there is this disadvantages of the extra work in tools.